Welcome to Biota Live. I'm Tom Barbalet, and this show is being recorded live on TalkShoe, June 5th, 2009. This is also a continuation of the Biota podcast. For more information on the Biota podcast, check out biota.org/podcast. That URL is also particularly important if you'd like to participate in the Biota Live shows, because we're now doing them via TalkShoe. We have two people in the chat already, including Rudolf Penikoff, previous participant in Biota Live, so it's good to have those two folk there. The last show, the chat was just on fire. I couldn't actually keep up. So if you're interested in listening into the show live, participating live questions via the chat, the place to go is biota.org/podcast, and it'll give you all the details with regards to how you too can participate in Biota Live, recorded 8 p.m. Pacific every other Friday night. So the next episode on June 19th is value in artificial life. This is actually going to be the topic that I do for Grey Thumb Silicon Valley, but I wanted to start it out on Biota Live to give some introduction to my thoughts and also to allow the participants to talk about the broader value of artificial life. I've had some correspondence with Mark Bedot over the week about setting up a special interest group as part of the International Society of Artificial Life, relating specifically to the addition of value, both through the academic community and also artificial life as it's used in industry. I'm going to have some news and notes, and then we'll get William R. Buckley on the call. I now do the shows a little differently, just some inside baseball. I record the pre-show news and notes before the actual show starts, so if you'd like to participate in that, the chat room's open. It's being recorded live via TalkShow, but it just allows for a little bit more discussion through the actual show. So, some news and notes. Biota 5. In 2011, this is going to be hosted by Dick Gordon's University of Manitoba, by the looks of things. I also mentioned that to Mark Bedot, because Mark Bedot's a little bit like Billy Crystal, basically, the artificial life community. You can't really have a show without Mark Bedot participating, so it'd be nice to have Mark involved. The three tracks I've talked about with Dick are the origins of artificial life, which is obviously Bruce Davis' EvoGrid project in some regard, probably will follow on from his Artificial Life 12 conference presentation and track actually associated with the EvoGrid. An artificial life perspective in the dialogue between science, philosophy and religion, which is obviously the Dick Gordon book project as previously described, and bridging the gap between artificial life in industry, academia and as a hobby. And this one I was thinking about in the discussion with Mark Bedot, that there may actually be a game subtract associated with that, potentially talking about things like Spore or the game SDK or artificial life developers tuning their algorithms for games or all this kind of stuff. So if that's of interest to you, then Biota 5 might be the conference to attend. Dick also mentioned that he was going to get grants and possibly sponsorship and things just to make it cheaper for artificial life participants to attend. And that's always a good thing. I think our community is spread out over the world. Obviously, I've Rudolf Penikoff in the chat, but there are a number of other artificial life, dialogue participants, members of the Biota community that live all over the world. And if Dick Gordon can make things a little bit cheaper for the folks to get to Biota 5, so much better. So it was always a good thing. So, the visions of the EvoGrid. We recorded the first of these discussions with Scott Schaefer last Sunday. And what I'm going to do is I'm actually going to do it out of phase. So, we're going to do Biota Live one week, and then I'll do a Visions of the EvoGrid recording the next week. I asked for folks who were interested in, what went on in the first recording of the Visions of the EvoGrid to give some correspondence and feedback. I got quite a bit through the week. It was fascinating. It was a great opportunity to chat with Scott, actually. I think I've had some correspondence with Bruce. I want to get a few of Bruce's friends outside the Biota community. He has some mathematician and physicist and biochemist friends who I think would be critical getting involved. Obviously, Freeman Dyson. I mean, if we can get Freeman Dyson involved in any kind of Biota podcast, I think the story's over in many regards. But our next participant is particularly interesting. Natasha Vita Moore has, I guess, recently come into the communication in the Biota conversations. Very, very interesting woman. Director of H Lab, which is a science and artistic design collaboration She's a PhD candidate at the University of Plymouth. And if you just put her name, Natasha Vita, as in Rita, but with a V and more, just with one O, into Google, you'll see a variety of videos of presentations that she's done previously. And we have William R. Buckley in the chat. I'm just doing the news and notes, William. For folks who are listening in, Rudolph just mentioned that I should include Lorenzo Haggerty in the chat, in the Visions of the Evo Grid. I have contacted Lorenzo. He's currently recording an audio book. However, I've said to him that there are 9 months that are open, and certainly we want Lorenzo to participate. William, it's good to have you on the call.
Yes, hello. How are you doing?
Pretty good. We're doing a slightly new format with regards to the news and notes. It just gives us more of an opportunity to chat. So I had one last part on the news and notes with regards to Biota Eve, and then we can get into talking with you.
Sure.
So the final topic in the news and notes is Biota Eve, and this is a project that was previously called Biota World and then Biota at Home, and then for a period of time it was called the Evo Grid Broad. But basically it brings together simulators to, I guess, brainstorm initially with XML phenotype formats from their simulations. And I think what has come through so far, Gerald Young's Darwin at Home, Scott Schaefer, who was on the show, or who was on Visions of the Evo Grid, the inaugural Visions of the Evo Grid, and I have all thrown in our XML phenotypes and are currently discussing how these things are going to fit together. There was an interesting post today from Gerald de Jong with regards to linking space and time in these various simulations together. And as I said in the inaugural Visions of the Evo Grid podcast, whilst things like space and time and energy and these kind of things all seem relatively trivial when you look at the vast diversity in artificial life simulations, they really are a starting block. They're a way of getting people actually thinking about how these kind of simulations can collaborate. Firstly, I have to apologize, William, because we've tried to get you on, I think, since probably early March, and through a variety of factors, we haven't actually been able to bring it together. But it is wonderful to have you on Biota Live. And for folks who aren't familiar with your work, I know you've been a very active participant in Dick Gordon's Second Life course, but for folks who aren't familiar with your work, can you give some introduction to who you are and how you first got interested in artificial life?
Well, actually, the way that I got interested is kind of a roundabout. I had in 1982 written a program that has a very interesting characteristic. It performs what's known as dynamic self-relocation. And what that is, in general, when programs execute within a computer, they sit in one location and work with data that is in a different location in memory. What this program does is actually manipulate itself. So it's a self-modifying program. And in so doing, it moves itself from one location in memory to another location in memory and then jumps to that new location. So it's constantly moving itself around within the memory of the computer. This has a very interesting visual analog that you can find in Douglas R. Hofstadter's book, Gödel, Escher, and Bach. You'll have to hunt around to find the particular reference, but basically it's two circles which have arrows that point to each other. In order for a program to do that kind of thing, it has to execute very carefully because it might manipulate its instructions in such a way that the instruction is no longer executable, and then the program stops functioning. That program, the Apple Worm, was later on published in Scientific American. Subsequent to that time, it turned out that Chris Langton had apparently fallen in love with a variety of similar models, one of which is, for instance, Core War, and that is a computer programmer's game where the basic goal is for your program to find my program and cause it to stop executing before my program finds yours and causes it to stop executing. Dueling computer viruses is a simple, abstract way of thinking about the game. So in all of these activities, the Apple Worm being published in Scientific American along with Core War and so forth, Chris Langton was motivated to contact a variety of us and invited us to participate in his upcoming conference or workshop, the Artificial Life Workshop 1, which was held in September of 1987 at Los Alamos National Labs.
And you had a mentor called Jim Hauser. Would you like to talk a little bit more about him?
Well, it would be interesting to do so. The unfortunate part is that Jim Hauser's no longer with us. He died, I think, in 1989. But that's related to the apple worm. Essentially, when I went to Cal Poly SLO for my undergraduate degree, Jim had just started there as a professor in the physics department where I was enrolled. And we got to be very good friends. He spent most of his time trying to figure out how to use the computer for educational purposes. And in fact, one of the common programs that's available called Type Attack is a product of that interaction between myself and Jim. But the apple worm came out of that particular interaction. One night, Jim came up to me and he asked me, putting his hand on the left side of the computer screen of his Apple, he said, write me a program that does this, and he moved his finger from the left side of the screen to the right side of the screen, and that told me internally, I could understand what his point was. I said, you want a self-relocator, and so I wrote that overnight. We got involved in some Core War, but he was not really that interested in that particular game. He was much more interested in using the computer for teaching and spent a lot of his time just prior to his death working on a tool, the space-time simulator, which would allow just about anybody to understand the mechanics of space-time reality in terms of a game. And it was never actually sold. Unfortunately, he died, and so it kind of went into the ether, as it were.
And for folks listening in, obviously, Core War is kind of, in some regard, early artificial life bread and butter, but could you explain to folks in the audience who haven't heard of Core War what it's actually about?
The basic point of Core War, as I explained, is that each person who plays writes a computer program, and then you introduce this computer program into an artificial computational environment. It's simulated. The problem is, how do you multitask with a lot of different programs trying to cause each other to stop executing when you don't have a controlled environment? It doesn't really work very well. People have worked on that problem since the invention of Core War, and I imagine that you can find some similar games. I've pretty much receded from the Core War environment since 1982, so I don't really know what's going on these days. But if you create a simulation environment for executing programs, and each program gets a certain amount of time of the simulator, then essentially you have an even, or as they might call it, level playing field. And then the programs are designed to search through the main memory of the computer in which they're executing and try to find opponent programs, and by manipulating the instructions of those component programs, cause them to stop functioning.
There's quite a fine balance, isn't there? I think the simplicity of Core War was actually part of the success. In having these kind of environments, you need a relatively simple set of instructions in order to mean that there will be some chance of these programs persisting when, large sections of them have been blitted out by opposing programs. That's one of the many principles behind Core War, isn't it?
Well, the simple point is that it doesn't really matter what the instruction sets are. You could have a very rich instruction set. You could have a very simple instruction set. The beauty of having a simple instruction set is that the simulator itself is relatively simple to construct. But the subtle point is that instructions within a main memory of a computer are ordered bytes that are retrieved or sampled for their value at regular intervals, at appropriate intervals. And if the arrangement of the bytes does not correspond to something that actually can execute, then the program will not function. In Core War, there's one instruction which is of this form, and it's an instruction designed to only store data and not actually to have some kind of operation that's performed. Typical operations would be add, subtract, compare, jump, that type of operation. And, it doesn't really make any sense to have something that executes and says, I'm just data. It doesn't mean anything in terms of a set of operations. So that's how Core War is actually constructed. You have a variety of instructions, one of which is not executable, the rest of them are executable, and so it is a fairly well-ordered and structured environment in which to effectively cause another program to stop executing. If you compare that to the instruction set of, say, the x86 or the 6502, some microprocessors don't have unexecutable combinations of bytes. They'll all execute. And some microprocessors have combinations of bytes that do execute and some which don't execute. But it really doesn't matter how many operations are involved in the game Core War. The real key is that there's a certain regularity to how it's implemented, and that makes writing of programs and targeting of programs a much simpler task to engage.
You attended the first A-Life conference in the late 80s. Coming from where you'd come from Jim Hausler, coming from developing Appleworm, what was your sense of the first A-Life conference?
Well, at the time, the ink on my degree was barely dry, and it was rather interesting to watch the variety of simulations and examples that people had concocted. Of course, it pretty much all was non-real examples. Very few people were doing work that would now be called wetware A-Life, the type of thing where you're trying to create a new bacteria that didn't exist before, engineering a bacteria from scratch. There are a lot of projects like that now going on. An example would be Proto-Life. But, there were a lot of different examples. Larry Yeager talked about some things that he had been doing at Apple Computer. I think it was called Vivarium Project.
Certainly.
And, they all had their characteristics that were interesting. What I found most interesting is the response of Richard Dawkins. He began his talk with an interesting statement, and I'll never forget the exact quote. There are some embryologies that are pregnant with possibility, and then there are some that are not. And after he opened with that particular statement, he spent 45 minutes on a tirade about being a dyed-in-the-wool Darwinian. And I didn't really understand his purpose at the time, but he was trying to describe why he felt a certain way about the different models that were being shown. And in closing his talk, his comment was that of all the different systems he had seen at that Artificial Life workshop, Core War was the least cheat model. And his real point was that, we had set up in Core War essentially an arms race. And we were missing some components, but everybody else tried to actually engineer examples of living systems, and we weren't really interested in doing that. We just sort of wrote simple abstract programs and put them into an environment and let them thrash it out and see how well they did. And that has led to, of course, the Tierra project and Avita, which are pretty much improvements on the abstract of natural selection, competition for the fittest, for survival over time, and involve examples of genetic improvements.
Now, from the first A-Life conference, I think what fascinates me particularly with regards to Dawkins is at some stage he kind of voted with his feet in terms of artificial life. But as you saw from Artificial Life, from the first Artificial Life conference moving into the early and mid-90s, what were you doing? And in parallel, what was your sense of what the Artificial Life community was doing over that period?
To tell you the truth, I'm not that involved in the Artificial Life community.
But as an external observer, what was your sense over that period?
a lot of this stuff with genetic algorithms and so forth is not really that impressive. I've been a critic of trying to engineer solutions. I agree with Dawkins that you should be able to see things develop on their own. One of the problems that I see is opportunities for intelligent design people. The basic argument that intelligent designers will give you is that you are putting into the system that you design the features that come out. And to a certain degree, I can buy their argument. We set up these systems, the A-Life community sets up these examples with, in some sense, intention of observing certain kinds of behavior. And that doesn't really jibe well with what goes on in biology, what the view of biological systems are. And that's really all I have to say about it. The problem is engineering the solution such that it displays the kind of behavior that, in a sense, you put into the system in the first place. The way you build your system, you get the kind of behavior out that you could predict. I think Richard Gordon has complained about that himself with his paper of, I forget the exact title, but something surprise. You put something in, you watch certain kinds of emergence, and you act surprised about the result when really you perhaps shouldn't be surprised.
It's funny because I think the artificial life community, as I have observed it, has been converted to this notion really in the past 5 or 6 years. And as you say, in some regard, it's taken prodding from the intelligent design community, also the panspermian community. I'm not sure if you're familiar with Brig Kleiss at all.
Yes, I am.
In his prize. But, we've had all these kind of external factors that have kind of prodded us in this direction to the point where it's now pretty actively recognized. I think what was interesting, I'm not sure if you heard last year when we had Ed Salford on from Eli Lilly, he's using artificial life as a search algorithm. He's using elements of genetic algorithms primarily, but also other aspects of artificial life to search these vast quantities of pharmaceutical data in order to find, novelty for future research. It's far faster than hand searching. And there is ultimately, as you say, the fringe of, or the best power for these kind of algorithms, but it's so far removed from what we want to, talk about in contemporary artificial life that I think that I wouldn't necessarily say kicking and screaming. I think certainly those of us with some kind of philosophical bent, found this a priori quite some time ago, but certainly with continuous instigation. What do you think this means contemporary artificial life simulation should look like with this kind of criticism?
In some sense, what you'd really like to do is to just turn on your computer and without introducing any other component, any program or otherwise, be able to observe the emergence of software. Now, I've thought about this for a long time, and I have a rudimentary example that I had worked on for a little while, but I've kind of dropped it. I've had a variety of other things to do. But if you were to look on SourceForge, you will find a project known as Evolution Design. That's the name of the project. The notion I have is this. If you look at the way the Earth was posited 3.5 billion years ago, you have constant bombardment with various sources of energy that trigger chemical reactions between atoms and simple molecules. How can you get something of a similar nature in a computer? The only example that I can come up with is what is contained in the idea for evolution design. What you do is you randomly seed the memory of the machine with instructions. Doesn't matter what they are. And then randomly jump into the seeded memory trying to execute programs. And over time, for instance, you start at a particular address by jumping in and executing at that address until you find an instruction that doesn't execute, and then you stop. Then you jump to a different address and continue on. And you do this process over time. What will happen is these instructions will tend to manipulate the content of memory, and in such a way that eventually you get looping structures. So how do you interpret that? And the way I think about it is that the instructions that are manipulated and changed develop looping structures which cause the longevity of the computation to increase. That's essentially what a program is. How long does it continue to execute? And if you followed a model that's of that nature, over time you would probably see programs begin to develop that have more complicated features. And they would tend to manipulate themselves a little bit less, so that the instruction sequence would tend to stabilize in some sense. And by randomly choosing the place where you start execution, you will cause interactions between these different small programs as they develop. And in that way, you might actually be able to say in a computational environment that you're observing some emergence of a living system. And if the programs can then develop skills such as translocation, that is, performing self-relocation, or manipulating other programs so that when the other program gets some of the execution stream, it is captured and brought back into the initial program. Say you've got two different areas, program A, program B. So program A manipulates program B such that when B gets some time from the processor, when it is initiated into execution, then the processor is directed into program A. And so program A captures some of the energy of the system, of the computing environment in which it's executing. That would be a reasonable model to me of evolving and emerging living systems, as opposed to the programmer directly writing a piece of code and putting that into the memory of the computer and having it battle with other programs.
So this is ultimately the idea of Avida or Tierra starting with random noise and then seeing what comes out of that, or it's even more fundamental than that? Actually,
that's not a bad analogy. I'm not so sure how well it fits with Avida. Tierra, I think that's probably a very close analogy.
Now, you've been listening to the discussion that Bruce Damer has put out with regards to the Evo grid, probably through not only the discussion through the Biota podcast and Biota conversations, but also through Dick Gordon's seminar in Second Life. I mean, do you think this is fundamentally the model of the Evo grid, or do you think Bruce Damer is doing something considerably different?
Well, actually, I'm a bit of a critic because I don't really see much coming out of it yet. The Evo grid, to me, looks not much different than, say, Second Life. I don't know what the real goals are, and so I'm probably not qualified to really comment. But my criticism is that I don't see it doing anything. I don't really get the impression of living environments. They're still simulations, and they don't seem to involve any kind of natural selection or that type of thing.
But I mean, the same argument could be made with regards to your example, because it's fundamentally existing in a very kind of state-oriented computer-centric kind of logic paradigm, which doesn't really exist in the real world either. I mean, do you think there is any kind of relationship that can be generated under these kind of instructions, methods that can map onto the real world at all?
I think they're analogous. You can find analogies, but, sometimes people carry analogies too far. And even the evolution design model that I abstractly described here, it just doesn't really feel that good. There may be some value to it, but I ultimately am worried about how much the human designer puts into the system in the first place. It's a double-edged sword. You wonder what you should do, how much you should put into your models. You wonder about the consequences of putting anything into your models, your predispositions, if you will. And I don't think that there's enough discussion of that. In fact, I think that the artificial life community pretty much is ignorant of relevant philosophy. And I really think that a lot more time should be given to consideration of philosophical questions surrounding the models that are built. Honestly, I think that A-Life could do with a real solid dose of philosophy. And as much as people like Mark Biota try, I really don't think that the rest of the community pays much attention to philosophy, and it ought to.
No, I completely agree. We have a comment more from Jeff Sphera in the chat. I understand Jeff hosted the 1987 Core War National Conference, so I guess you know Jeff in times gone by. He was asking the question whether any of this needs to map over to the real world, and I think that in itself is a question. But I mean, expanding this idea of philosophy a little bit, I mean, I think certainly we've had Larry Yeager on talking, and we've also had Mark Biota on talking about the idea of an artificial life curriculum, what it should contain. And I mean, my recollection of that is we talked a little bit about cellular automata, but we didn't get into Core War specifically. What would you like to see kind of, contemporary students that are studying artificial life to learn about things like Core War?
Core War is simply a good model. It would be a good example for students to understand some relevant issues, especially if the model included things such as genetic algorithms and genetic programming. The good example that I can give, which has been published, is the work of John Perry, and I don't have a reference to it immediately. I probably have it on my computer here, but basically, coming up with the use of genetic techniques like crossover and mutation to develop and improve the line of programs. And I know that there is some work that still goes on in that area. But I don't think that you can draw too many strong conclusions from Core War, honestly. And I think that was some of Richard Dawkins' point. He said that Core War was the least cheat model, but he didn't say it was a good one. And he didn't say it was ideal. I think he was really trying to cast doubt to all of the other participants regarding the value of their own models. I don't think that he was trying to hold up Core War as being a particularly exemplary model. And I don't really think that there are any really good models. In every case that I've seen, a lot of it seems a bit contrived, even in Avita.
It's very difficult philosophically to move away from this whole notion of things being contrived, I mean, particularly with regards to the simulation constraints. And I certainly agree with you that artificial life needs a solid and fast dose of philosophy with regards to these kind of issues so we can start creating better simulations that can answer these kind of problems. In terms of,
avoid creating we don't need to create the simulation. We need to instead understand how things occurred in nature and try to build models that are much more like nature. The value of the computer is the speed of its computation. And, it takes 1 billion years or 4 billion years to observe evolution on an Earth. And yet we might be able to see it happen within a computational environment in the lifetime of a human, or maybe in a weekend. But you don't want to bias your models so that it gives you what you're expecting. You want to have the model show you what's possible, and do so with as little input from the human as possible. And that's really where the tension is. we tend to bias our models quite heavily, and we act as if there is no bias. That's the problem with artificial life as I see it.
Agreed. We have Rudolf Pennikov on the line as well. I might just bring him in. So I'll ask the question and I'll bring him in at the same time. Hello, Rudolf.
Hello, Tom. I finally was able to dial in.
It's good to have you on the call. As you know, we have William R. Buckley. I know you've talked to William in Dick Gordon's Second Life course. I'm just going to ask William a question, and then I'll allow you to throw out your own ideas and questions as well. But as I was saying, William, we have a number of students, undergraduate, graduate students, who listen to this podcast. And as you say, artificial life needs more philosophy currently. What is your recommendation for these students to be better artificial life practitioners? What kind of philosophy should they be reading? What should they be thinking about, in your view?
Well, I can tell you what I'm reading these days, and that's biosemiotics. I picked up a book by the man Jesper Hoffmeyer with the title Biosemiotics, and it is very interesting in its analysis of what living systems are versus the neo-Darwinian paradigm. And frankly, I think that neo-Darwinism is overblown, over self-important, and does not really convey to the human mind exactly what the nature is of living systems. Living systems have holistic qualities that cannot be analyzed with reductionist philosophy. And we really do need to understand these complicated interactions between parts and wholes. And much of biology for the last 150 years has been all about parts, with complete ignorance of the wholes. Marcello Barbieri, I believe, is correct in his assessment that there are more than the genetic code involved in living systems. And this particular book does a very good job of detailing all of the relevant issues. And I would recommend that, in fact, anyone who is serious about artificial life should start with philosophy, and particularly philosophy of biology and semiotic theory.
Very good. So what you're saying fundamentally is that Dawkins in the late 80s was right, but contemporary Dawkins is wrong.
Dawkins gave some very good ideas, some good starting points. I was quite impressed with The Selfish Gene. But I think that he's moved away from the core. He's analyzed a lot of interesting issues, and he's posited many interesting ideas. But I don't think that his ideas alone are correct, and I don't believe that the reductionist program is the right solution for understanding living systems.
Agreed. So Dawkins should be on the bookshelf, but also should be shared with a wide variety of other authors.
Yes, absolutely.
So we've lost Rudolf from the call, but I mean, I want to move from this period that we're describing to the present day. You have a current development that you're very excited about. Would you like to introduce that to the Biota community?
Sure. The real father of artificial life is not Chris Langton. Chris may have coined the phrase, but ultimately, artificial life as a field derives from the work of John von Neumann. I have been fascinated with von Neumann's cellular automata since about 1972 and spent an awful lot of time studying it. Indeed, one of the problems with his model is that it is very computationally intensive, and only in the current decade are we able to see performance of simulation software that is capable of demonstrating, say, self-replication within his model on a reasonable time scale. There is a product called Golly that you can get from SourceForge, which is a simple cellular automata simulation tool. It has been extended to support more than the game of life, and now will support a whole variety of cellular automata systems, COD, von Neumann, extensions of those. And within that environment, you can see some of this work. So now it occurs that there are self-replicating cellular automata configurations that do perform self-replication within a reasonable amount of time, 15 minutes or so, on a contemporary computer. The problem with those kinds of models is that they're all holistic. That is, that the mother configuration constructs all of the daughter and then turns the daughter on, and the daughter then performs its own self-replication by constructing its daughters. But that's not really how living systems work. The way a living system really works is that, except at the single cell level, when you're talking about bacteria and so forth, it turns out that higher organisms, humans, they create eggs, and these eggs then go on to develop into the whole organism, or at least that's what they're supposed to do. The question has been, how do you build a machine? Because that's what von Neumann models are. They're machine models of self-replication. How do you build a machine that is able to construct an egg? And I have one model. That particular model is described in a paper called Computational Ontogeny that you can find in the journal Biological Theory. And there is, to date, only one such model. The way this works is by a process I call partial construction. So in this case, the mother creates a small but critical portion of the daughter and then turns that on and retracts from the daughter. So the mother doesn't influence the daughter at all anymore. After that, the daughter then reads its tape, and maybe I could go through a description of how these machines actually look, but it reads this tape, and from the tape it is able to construct all the rest of itself. But it needs all of itself to be fully constructed before it is then able to construct its own eggs. And that's a very different notion of self-replication, machine self-replication, than von Neumann had envisioned. So essentially, what I've been able to do is build a machine zygote. And the analog to the real world that I see, it looks to me like a seed. If you take the average seed and break it in half, you'll find that within is a small plant. And everything is there, some leaves, a little trunk, except there are no roots. And, of course, there must be some connection to the endosperm of the seed, but there is no real root structure. And when you plant this, the roots develop, and the plant, the small plantlet, essentially a homunculus, grows itself. And that's pretty much what occurs with this particular machine model of self-replication.
So we have Jeff Spira in the chat asking about sexual maturity in this model.
Well, these particular configurations do not have sexual format. The only person that I know who has really looked at sex within machine models is Paul Vitagni, and I have studied his papers, but I have not yet been able to incorporate his work into my own. I'm sure that it must be possible, but those are going to be much, much more complicated configurations than what I'm working with now. And I might say that within the cellular automata of von Neumann, his 29 states, these configurations are actually quite large. They will be several million cells, and that's exclusive of the tape. The tape is just let me describe this in a sense. The configuration itself will be of some extent in 2 dimensions, but the tape is a one-dimensional appendage that strings out for an awful long time. And the tape will be composed of instructions that are represented by a certain number of bits. Think of it abstractly as bits. And it corresponds that the number of bits per instruction is 5 or 6 or 7. Efficiently, you can do it in 4, but it's not very easy to accomplish that goal. So we'll just say that it's 5. And it turns out that you will need approximately 3 of these instructions to describe every one cell of the configuration. And so if you have a configuration that is 1 million cells, the tape itself will be 15 million cells. And as a result, it takes an awful long time for these things to execute.
Well, we have Rudolf Penikoff back on the line. Rudolf, as you listen into this evening's discussion, do you have any questions for William?
Yeah, I think it would be probably better to focus a little bit more on the environment for the artificial life rather than on the life itself. Do you have any comments on that?
Actually, that's a reasonable interpretation. Remember that there are two sides to living systems. There's the genetic component, and then the component that is the whole real living organism, the cell itself, all of the parts within the cytoplasm and the cell wall and so forth. So you need to have a complete or holistic view of these systems instead of just a reductionistic view. The reductionist view is the view of Dawkins, who concentrates on the information which is represented by DNA. And I'd like to point out, DNA does not contain information. It's just a molecule. The sequence of nucleic acids that comprise that molecule as a sequence represent the information that DNA makes available to the environment in which it is a part, which is the cell. So you have the genetic component, which is a representation of information, and you have the machine component, which interprets that information. And both of those parts have to be considered together. And I think it's really wrong in the work of Dawkins to concentrate only on the DNA itself. The rest of the cell is important. In fact, it's the major
I would agree
component.
Here. Indeed. But yeah, I would like to stress that we shouldn't try to simulate living cells, because then that's going to be nearly impossible.
The problem is not that it's impossible. You must recognize that the price of computation, the price of storage is going down. It has been going down ever since computers were first built, and it will become vanishingly small. The throughput of machines is growing almost without bound. That's kind of Moore's law. So we have plenty of computational resources, if not today, within the very near future. The real problem is what you put into the model. How much do you bias your model? The real issue is bias.
Agreed. But shouldn't we just work with an evolvable instruction set, or rather instruction sets of which the best evolvable instruction set is selected upon, rather than try to simulate biological cells or something like that?
Actually, you get at something that seems reasonable, and as a computer scientist, I can say what you're talking about is a microprogram that over time evolves so that the instruction set that is supported by the computer is more and more capable, gives you more and more features, gives you more interesting features, something like that. And that seems like a reasonable approach, because you are interacting the macro scale with the micro scale. And that is more inclusive. It gets to be more like living organisms. That's what the problem is with the EvoGrid. I think that there's too much bias in the system. There's too much defining our expectations instead of simply waiting to see what happens. That's what occurred in nature. There was enough time, and we waited to see what happened, and in the end, you had the universe able to look at itself through the agency of human intellect.
Indeed. Also, a big part of nature is that there's always a new challenge just around the corner for life that's emerging. I mean, when love crawled out of the sea might be a very interesting example. I mean, there's new challenges all the time, and I don't see that in artificial life as in a complex environment. Always in programs like Tierra, there are very few challenges for the life itself, unless the life forms interact and try to compete for some resources. Then that interaction might make the environment a little bit more complex, but it's not selecting for anything that we would call very useful, like finding solutions to problems.
Yeah, there's another thing that I observe, and that is you can find examples that are analogous to niche selection, niche creation, but you don't really see the kind of dynamic interaction that within artificial life models that you see in the real world, in physical life. And it is the fact that organisms not only move into niches, but they modify the niche. And when they modify the niche, they also modify the selective pressure upon themselves. And so there is this ecological concern that doesn't really come across in most of the A-life models that I've seen.
Definitely. You might say that a living cell is a niche for the replication of the information in the DNA itself.
That's a reasonable interpretation, sure. So switching things up a little bit, William, how did you first start corresponding with Dick Gordon?
I'm not exactly sure. What I could do is search through my email and find out when I first tried to correspond, but I can say that the Internet has been a boon to my research. Probably in 2001 or 2002, when things really started to come together, email and other mechanisms, and I was able to browse the web and find the work of other people. I'm pretty gregarious, and when I find someone who's doing some interesting work in which I find interest, then I just pick up the phone and call them, or I will send them email just out of the blue and try to strike up a relationship. I can mention many, many people. One in particular is Danielle Monge, who used to be the director of the Logic Systems Laboratory at the École Polytechnique Fédérale de Lausanne, which is in Switzerland. And he found interest in my work in cellular automata, particularly von Neumann cellular automata. And at the time, I was reasonably close to having finished my graduate degree at Cal State Fullerton. So the problem is that at Cal State Fullerton, no one understood anything about cellular automata, much less von Neumann's work. And it was very hard for me to find like-minded individuals. I had to reach across the world to find one. He befriended me, and we got to talking about a lot of interesting issues, and he could recognize that I was coming close to actually having a self-replicator within that system. Little did I know that it actually would perform partial construction. That was kind of a flash in 2005. I was thinking about the model, and I suddenly realized that it would perform in this particular fashion. Let me give you there's a paper that's published in the Proceedings to Automata 2008. I didn't actually attend the conference, but this 50-page paper is in there. One of the problems I had with this paper is that it is so large, but you need it to be that large in order to actually address all of the attendant issues of self-replication in von Neumann's environment. So it was hard to find an appropriate venue. I sent it initially to the Journal of Cellular Automata, and it was rejected roundly. But one of the things in the rejection letters that I got was a comment that said that this paper presented no new vista. That's the quote, no new vista for cellular automata now or in the future. And that particular comment really irked me to no end. In fact, I found it to be rather insulting. The reason is because there was no recognition of what partial construction was. I didn't really give a full description, but I did describe, in a page and a half what I was talking about. The problem is the paper was already huge, and no one wanted any more pages added to the paper. It's very, very dense material. So I asked the reviewers, I commented back, I replied to their rejection letters, and I asked them in a challenge. I said, go out and find any self-replicating cellular automaton that's been published and convert any 10 cells, exclusive of the tape, from their non-ground state into the ground state, and then show that it still self-replicates. I'm still waiting for a counterexample. There hasn't been one presented. In the case of my partial constructor, It's, as I say, about 1 million to 2 million cells in size. And you need all of those cells to be constructed in order for it to be able to build a replicant of itself, even to be able to build its seed. However, you only need 20% of those cells to be constructed for it to be able to build the rest of itself. When I was a kid and talking about biology in high school and junior high school, one of the comments that I remember from my teachers is that, and this was when they were first starting to think about the genome as a sequence of instructions, literally as a computer program. That was the model coming out of everybody's head. And the question was, how do you encode all of the information into the genome such that it can then build, a whole organism? The question is encoding. And in order for you to build a partial constructor, you must have much more encoding than you need for a holistic self-replicator. That's the real key. If you understand how encoding can be pushed into the tape as opposed to having to be explicated in a complete construction, then you will understand how partial construction works. And I think it has some relevance to biological models. In particular, a researcher in South Africa has recognized that the model of partial construction has ontological implications for the status of viruses as a living organism.
And certainly a lot of this overlaps with Dick Gordon's own dabblings with regards to digital embryology as well. I mean, this is what fascinates me with your connection with Dick. I mean, you say that you started corresponding with him in around 2001, but have you had greater and more meaningful correspondence up to his current Second Life course?
Yes. In fact, Dick is an embryologist, and he understands embryology very, very well. He has devoted his life to a particular model organism, which is the axolotl, but he's much more interested in the physical environment in which development occurs. There are some other interesting people within the course. Vincent Fleury, who is in France, I don't know exactly which institution he's in, but I believe it's the University of Paris. And he tends to be much more concerned with the physics. Richard tends to be much more concerned with the chemistry and the mechanics. My interest actually is primarily in trying to understand how organisms develop with an eye to abstraction to physical models that do not involve nucleic or amino acid-based chemistries. I'm literally interested in building machines of non-biological form which go through developmental processes, which produce children, and which are therefore subject to the effects of natural selection. So what I've done is run around looking for people who have similar interests, who will tolerate my eccentricities, and perhaps facilitate my ability to understand how real-world biological organisms go through a developmental process so that I can abstract those processes and impart them into physical machines.
So with 6 minutes remaining, I'm interested in taking your particular perspective with regards to the future of artificial life, but I'd also like to frame this in some regard. I mean, my understanding is that you're the quintessential artificial life hobbyist in terms of someone who's been doing this for a number of years, who submits papers to both conferences and periodicals, but really, I mean, you're not an academic, are you? Artificial life is not your day job, it's just your passion.
It is my passion. My day job is I'm occasionally a longshoreman. I've been a computer programmer for a long time. Actually, at this point in my life, I'm probably retired. But, and I'm looking at going back to school. In fact, if things work out, I will probably pursue a PhD program with Richard and do it in Manitoba, primarily thinking about genetic regulatory networks, because I think that that's the place I need to concentrate in order to abstract as best as possible and apply it to my physical models.
So
I'm not really an academic. I'm a closet academic.
Well, I think that's the nature of all artificial life hobbyists in some regard. But
they won't let me in.
That's exactly the point. But I mean, in terms of your vision for the future, how do you integrate what is a growing and even more dynamic artificial life hobbyist community, both with academia and also with industry? What's your vision for this?
Oh, I don't have any vision for industry. I really don't care what industry does with it. I'm much more interested in actually building these abstract models and watching a physical machine go through this process 3 or 4 generations in a row. You know, I have interest in philosophical concerns, in interesting questions. I'll give you a very good question. You tell me, is life an obligation? And I think that that's perhaps the most profound question anyone can ask themselves.
Well, if the tree falls in the forest, then obviously the observer is part of the question. Mm-hmm. So to even ask the question requires life to be an obligation in order to observe the question.
Well, part of the question is, do you have an obligation to live? Do you have an obligation to pass off to another generation the opportunity to live? Those kinds of questions are very heady, and if you start to think about them very much, you get lost in an awful lot of ancillary issues. And to me, I've already got my children, so I've accomplished part of that goal. And I'm almost at the end of my own life cycle, so I've accomplished part of that goal. Can I pass that off, the ability to live, to things that aren't related to either of those two environments? To myself, by not killing myself, the comment of, was it Albert Camus, whose comment was, the only question is whether you commit suicide or create children. I've accomplished those things, but now I'm thinking, is there any other way that life becomes an obligation that I should pass it off to, say, a physical machine? And I'd like to know, can you really build a machine that lives, which is not biological? The only other models that people have are the things like proto-life, and that's where they're trying to create living organisms by engineering them. Creating a cell, engineering it, designing the genome for a particular purpose, getting all of those pieces of the puzzle together so that it continues on its own. And that's one aspect. But I'd like to abstract it from the biological.
So, to throw that question back to you, consider 4 systems: the financial system, the road system, the legal system, and the system that we can describe as the internet, whatever that may be. Do you think that all these systems have properties of life that are non-biological fundamentally, particularly with regards to their ability to outlive us in our discussion?
Not the legal system, I don't think so. Roadways, perhaps, but probably not. When you get to automated factories, now you're getting there. I hear some people complain about the work of Hod Lipson, that it isn't really a self-replicator. I disagree. I think he's got a really interesting model. Most of his work looks like self-assembly. I understand that. But if you get these complicated robotics units that he's building with enough capability that they can stand at a lathe and mill out their parts, they can operate the machinery that we already have for building semiconductors and so forth. They can handle a soldering iron, and they can mine materials. They're getting very close to providing the kind of living system, physical living system that is non-biological, that captures my attention, because they'll be able to then operate all of the facilities, utilize the roads, utilize automotive transportation, that kind of thing, in order to facilitate their own bootstrapping. It kind of depends. Legal systems don't really seem to be it, because they exist through the facilities of the human mind.
But, however, they exist outside a human life cycle and completely independent of the humans that maintain them fundamentally.
Yeah, but they're more like the memes that Dawkins talks about.
So, as we have the benefit of Rudolph on the call, I'll give him the opportunity to ask William the final question for this evening. Rudolph, as you listen in, what is the pressing question for you?
Thank you, Tom. Well, I'd like to go back to industry and software companies. Myself, for instance, I'm really considering seriously to propose having them develop artificial life software which is able to meet some challenges. A little bit similar to what Stephen Taylor did in Imagination Engines. I mean, he writes good old-fashioned artificial intelligence, but it's neural networks which even come up with completely new ideas. And I think making artificial life useful in such a way that it will solve real life problems, it will drag it much more into society and creates a much bigger user base for it. What do you think about that, Bill?
That sounds like something which is biased with human intention. And I'm trying desperately to excise models of human intention. I don't know whether I'll be able to accomplish it. The partial constructor is a very interesting example, and yet there's an awful lot of human intention engineered into that solution.
Sure, but yeah, I would like to see artificial life ultimately evolving into a smart entity, and then it will have to be able to communicate with humans, and yeah, the human intention is very important in that, isn't it?
There's an expectation there. You say that it will have to communicate with humans. I don't think it necessarily has to communicate with humans. It might want to cut itself off completely from us, decide that we're a useless cul-de-sac in the evolutionary pathway.
Well, so far, I think we're the most interesting species that I know, at least.
We might be, but that, you have to admit, is a biased point of view.
Well,
other species may not think we're so interesting.
Yes, I own cats, and I think certainly cats think that they're the most interesting species. And rightfully so. I mean, I work for my cats. So. Anyway, rounding off the evening...
How does your wife feel about it, Tom?
Well, I work... Well, let's not go that far, Rudolph. Let's end the evening on a nice, calming note by thanking William. And look, William, you participated in last episode of Biota Live, and I really would like to have you back. I think your insights this evening have been particularly topical, and I think also historically a number of the things that you've talked about with regards to cellular automata, with regards to core wall, with regards to self-replication is lost in a lot of the contemporary artificial life narrative, which is obviously what you said previously as well. So, I mean, it would be wonderful to have you as a kind of continued participant in Biota Live.
I'd be delighted to participate. It will take a little time for me to warm up to the format and so forth. I'm doing an awful lot of reading these days, but I'm sure that there will be many comments that I can give in the future that will be relevant and insightful.
The nature of Biota Live is really to give a completely open forum. It's almost the anti-conference in that regard, and certainly, I mean, having folks like Rudolph and Gerald de Jong and obviously Dick Gordon, Bruce Damer. I mean, there is a long list of people that are regular participants in Biota Live, obviously Jeffrey Ventrella in the last episode as well. And what we're trying to do here is create an open forum of discourse, but ultimately, as I've said, it's used as an educational tool by undergraduate and graduate students currently, and they're also very welcome to participate. I'd also like to thank Jeff Sphera for participating in the chat this evening, and also would like to encourage Jeff to participate in a future Biota Lives. And Rudolph, it's wonderful as always to have you in the podcast. Do you plan on starting your podcast in the near future?
I do indeed.
I think we're all looking forward to that. The more artificial life podcasts, the better. And I think your particular angle and set of interests would be wonderful to have in a podcasting form. Our next Biota Live will be with regards to the value of artificial life, which ultimately tags into some of this artificial life in industry and obviously some of the stuff that William, Rudolph and I have been discussing this evening. The Visions of the Evo Grid will continue as well. I'm looking forward to having a number of future participants. If you're listening to this podcast and you've been listening to previous Biota Lives with Bruce on, if you've been listening to the talks that Bruce has done as we put in the Biota feed, and you have particular questions about the EvoGrid specifically, or if you have your own unique vision, which may in fact be completely independent. I mean, this is what interests me about Natasha Vita-Moore in particular, is that she hasn't been part of Bruce's discussion with the EvoGrid. She brings to the table kind of transhumanist perspective and a wide variety of big-name philosophies associated with this, so it's going to be very interesting brainstorming with her. I'd like to, again, thank William R. Buckley for the chance to chat with him this evening. It's been absolutely wonderful, and I look forward to having future chats with him and his kind of continued reading and instigation in the Biota community. And thanks also for Rudolph for calling in, and thanks also for everyone for listening.
Look forward to having another chat. You enjoy.